Hello everyone, welcome to Recitation Week 9 for CEE122 Fluid Mechanics. We will start questions with 6.23. In this question, we are going to determine forces in x and y directions needed to hold this fixed vane. So, which turns out to oscillate with a specific gravity of 0.9 in a horizontal plane. We have velocity 1, we have velocity 2, and we have the flow rate given. So basically we need to find fx and fy, which is the force in x and y directions. And let's see what we have. So we have this inlet mass flow rate, inlet momentum. And then we have momentum for outflow, and it is coming with 30-degree angle. So let's say mass flow rate times out velocity. So this is out momentum. So let's get started with the first one, which is horizontal. So we have this momentum equation for x direction. We have m dot, which is mass flow rate, out velocity in x at x direction, and we have mass flow rate, inlet flow, still x direction. So first we will start with out, and since we need to find x direction, we will have this horizontal component of this velocity. So it will be v2 cosinus 30. And as you can see, the question is taking this direction as positive. And since this is going from right to left, we will have negative velocity. So this gives us mass flow rate v2 cosinus 30 minus we have this inlet flow. So let's say m v1. So here we already know the velocity 2 and velocity 2, which are inlet and outflows. But we need to find the mass flow rate, which is m dot. So it will be rho q, which is density times flow rate. So density is 1 kilogram per cubic meter. And since this is not water, this is oil, and since the specific gravity is given, we can directly multiply it by 0.9. And again, the flow rate is also 0.9. So this is going to give 810 kilogram per second. This is just the mass flow rate, but we need to find horizontal force. So Fx will be equal to 810 kilogram per second. And we have minus 33, which is the velocity 2. It is already given in the question. Times cosinus 30. And here, now we will see the sign. Normally we have outflow minus inflow for the calculations. So the right x direction is positive. So we also have a positive momentum here. So again, it will be also positive, but due to this sign here, we will have negative velocity 1, which is 29 meters per second. And from here, we can get Fx is equal to minus 46.6 kilonewton. So this means the force is acting to the left. So this is the first finding from this question. We just calculated the horizontal force, and we also found its original direction. So even though it says this is the direction, since we find negative fx, it means we will have fx to the left. And secondly, we are going to calculate the horizontal force. So let's write momentum equation for y direction. So vertical forces will be equal to, again, outflow minus inflow. We have everything same actually. So we have out minus in. So let's look at the shape to see what we have. So as inlet, we don't have any vertical component, as you can see. We only have horizontal, so we can just ignore inlet. But we will have a vertical component for the velocity. So we will only take that. So as I mentioned, let me ignore this, which is the inlet, because it doesn't have any vertical component, it only has horizontal component. And mass flow rate is still same. And the out velocity is 33 times sine 30. And now we need to see its sign from the shape. So as the question stated, we have positive direction, positive y direction as upward, but here we have downward. So we can say this is minus. Sorry. And this is going to give minus 13.37 kilonewton. So this means we have Fy acting downward. This is also same with the horizontal. The question takes upward direction as positive, but we calculated negative, so it means we have downward vertical force. Let's continue with second question. This is question 6.56. Here we have a pipe and it has 180-degree horizontal bend, and the D is 20 centimeters, and D is this diameter here. The discharge of water in the pipe and the bend is 0.35 cubic meter per second, and density is also given. And this time we have pressure in the pipe and bend, and it is given as 100 kilopascal. The bend volume is 0.1 cubic meter, and the bend itself weighs 400 Newton. So what force must be applied at the flanks to hold the band in place? Sorry. So differently from the first question, this time we have force, we have pressure. So the pressure will always act into the control volume. So we will have pressure force here and pressure force here. And for example, if there were pressures in the first question, we will take pressure force here and also pressure force here, which is directly into the control volume. So since we have pressures, it means we will have pressure force. And when we are calculating this force, the force we need to apply, we need to also consider these pressure forces. So basically on horizontal direction, we will have P1A1 and again P1A1. And actually we can just say we will have 2PA. It is because they have the same size and same pressure. So we can just use 2PA. So let's look at the horizontal direction. So we have Fx, and right now we have 2PA. This is equal to out momentum minus in. So from here, first let me find the velocity, because we are going to need to find velocity here. So Q is given as 0.35 cubic meter per second. And because of the continuity equation, the flow rate entering this system will leave as it is. So Q1 is equal to Q2. And this is because the continuity equation, and also we have the same size here. So the velocities will be also same, because the flow rate is equal to velocity times area. Since we will have same area, we will have the same velocity for in and out. So let's find velocity. So velocity will be equal to flow rate over area, which is pi d square, and d is given as 20 centimeters, which means it will be 0.2 square meter divided by 4. And from here we can get V1 as 11.4 meter per second. So 11.14. And since in and out has the same diameters, they have same area, and as I mentioned, they will have same velocity. So V2 is also 11.14 meter per second. So let's look at the first equation here. So Fx plus 2Pa, which is the pressure force, will be equal to rho Q out velocity. And here we can assume this is the positive x direction. And since the velocity is going to the left, we will have minus velocity. So we have minus v2. And since it is out minus in, we will also have minus rho q v1. So q is same, rho density is same, so that we can actually write fx is equal to minus 2pa minus rho q and v. So let's see what we have. We have minus 2 times p, and p is the pressure. So to have the same units, we are going to use Pascal instead of kilopascal. So we have 100,000 Pascal times the area, which is PD square over 4. And this is actually giving 6,283 Newton. So Fx is equal to 6,283 Newton minus. Now we are going to calculate this one, this term. So we have 1,000 kilogram per second, which is the density. We have flow rate, which is given as 0.035 times the velocity 11.14 meter per second. And this is cubic meter per second. So from here, we will get Fx as minus 14.1 kilonewton. And now if you look at the vertical direction, as it is clear, there is no vertical momentum because we only have horizontal inflow and outflows, so that we will not have any momentum on z vertical direction. So we will have the weight of band plus the weight of water. This is given as 400 newtons. And for the weight, if you remember from previous recitations, we are going to use specific weight times volume. And the volume is actually given in the question as 0.1 cubic meter. So we will just do 0.1 cubic meter times the specific weight of water. And this is going to give 1.381 kilonewton. So the total force will be minus 14.1 I 0 J plus 138 K kilonewton. So actually let me correct this one. So here we are assuming a three-dimensional shape. So instead of y, we are using z. Therefore, we have x, y, and z. And we only have components at x direction and z direction. So that this is the final force. So this is question 3. We will continue with 6.71 in your textbook. So let's read the question. Here we have a horizontal T, which explains the shape. And we have water density is flowing. And we have the following data, which is Q1 that enters the system. We have Q2, which leaves this system vertically. Q3 is not given for now. And we have P1, P2, and P3, which represents the pressures at these points. And we also have diameter of each section. The given pressure values are gauge pressures, and for these conditions, what external force in the xy plane is needed to hold the T in the place. So as I explained in the previous question, we can start with the pressures given, because eventually we are going to need to calculate forces on horizontal direction and also vertical direction. So we also need to consider pressure forces. So as I mentioned, it will act inward to system. So we will have P1, A1, P3, A3, and P2, A2. So now we can continue the question. Here we need to find force, both x and y directions. And for each of them, we actually need to find velocity in the system, because we are only given flow rates. And also from continuity equation, we can write this. We have Q1, which is entering the system. And then we have Q3 that leaves the system, and we have Q2 that also leaves the system. So Q1 is equal to Q2 plus Q3. Q1 is given as 0.4. Q2 is 30. So this is actually 40. This is 30. And this will be 10. And actually, in the solution, we are using 0.4. So let me make it 0.4 cubic meter per second, 0.3, and 0.1. So you can also keep solving the question with these values. But I will continue with these values. So from here, we can get velocity 1, velocity 2, and velocity 3. So let's start with V1, which is velocity 1. So we need to use Q over A, and we will have 0.4 divided by the area of this section. So the diameter is given as 15 centimeters here. So we have pi times 0.15 square over 4, which gives 22.63 meter per second. Similarly, we will have 0.3 cubic meters per second. Pi, we have 0.7 centimeters. So it will be 0.07 square over 4. And this is giving 77.95 meter per second. And lastly, we will have V3. And this time we will have 0.1 cubic meter per second. We have pi times 0.15 square meter over 4. And this is the area, of course. So we have 5.66 meter per second. So we calculated all velocities in this system. And now let me write the horizontal momentum. So let's say Fx. So we will have all forces on the left-hand side and then momentum on the right-hand side. So we have Fx and we have positive PA, and then we will have negative P3, A3, and we will not consider this for now because it is vertical and we are doing horizontal. So let's say Fx plus P1, A1 minus P3, A3. So this is equal to out minus in. So we have m.3 v3 minus m1 v1. So from here, we will actually get Fx is equal to m.3 v3 minus P1 A1 plus P3 A3. So M3 mass flow rate, which is rho Q. So let's get started with this one. We will have rho Q V3. Actually, let me directly write numbers. We have 1 kilogram per second times Q, which was 0.10 times the velocity of 3. We have minus, now we are at this step. We have minus 1000 kilogram per second, which is density. We have the flow rate, and it was 0.4. And of course, we will have velocity, and we calculated it as 22.63 meter per second. And let me continue from second line. Now we will calculate minus P1A1. So for P1, we have 100 kilopascal, which is 100,000. And we have 70 kilopascal, and it is 70,000 pascals. So for P1, we have 100,000 Pascal times the area. So this is the area of this section again. And lastly we have P3, A3. So it was 70,000 Pascal times area. So it will be pi d square over 4. So we can write because they have the same diameter. And from here, you can get minus 8,840 Newton. Now look at the momentum equation for y direction, which is vertical. So this time again, we have Fy. So we have Fy plus P2, A2, which is pressure force. And we have out. So we don't have inflow. So that we will only use this outflow. And for that, let me write Fy plus P2 A2 is equal to out minus in. And there's nothing entering the system, so we can just remove that. And we will have m dot. So we will use rho QV equation. Here, again, the question says the upward vertical direction is positive, but we have a downward velocity, so we will have minus velocity too. So let me write that. We have minus, we have rho as 1,000 kilogram per second. We have Q, and we calculated it as, actually it was given in the question, as 0.3. And the velocity is 77.95. So here Fy will be equal to this value. Actually, let me do it something like this. So if we move this term, if the pressure force to the right, it will be minus P2. So P2 was 70,000. Times the flow rate. Sorry, area, because this is P2, A2. So we will have pi times D2, which is 0.07 meters square over 4. And from here, Fy is equal to minus 23.7 kilonewton. is question 4. Let's continue with 6.75. Here we have a propeller on a ramp boat, and it produces a slip stream 3 feet in diameter with a velocity relative to the boat of 100 feet per second. The air temperature is 80 Fahrenheit. And what is the propulsive force when the boat is not moving? And also when its forward speed is 30 feet per second. So we will assume that the pressure, except in the immediate vicinity of the propeller, is atmospheric. So that this means we can just ignore pressure effects, and we can just do our momentum calculations. So first, from table 8.3, you can get the density of air at this temperature, and it is 0.00228 slug per cubic feet. So we have two conditions. The first one is stationary boat, and the other one is when the boat is moving. So let me draw a control volume for this question. And here in the question, it says we have a slip stream, and the diameter is 3 feet. And its velocity and velocity of the propeller related to the boat is 100 feet per second. So based on this, we can do something like, actually let me, so we can say this is 1 and this is 2. So we have out conditions and we have in conditions. So when we have a stationary boat, we need to find the force. So momentum, we need a momentum equation, and in x direction, fx will be equal to m2 mv2 minus m dot v1. And here, since the boat is not moving, we don't have anything entering this control volume, so that the velocity term will be 0. So fx will be equal to mv2, which is out. And here to calculate the mass flow rate, m dot t, and actually mass flow rate will be same for all system, and it is because inside of this control volume we are using velocity relative to the control volume, so that we will use this 100 feet per second for mass flow rate calculations. So it is rho q, and rho is given as 0.00228 times pi d square over 4, which is 3 feet over 4 times 100 feet per second. So this is the mass flow rate for the system. And because this is the velocity relative to the boat, so we are using this as the our mean velocity to calculate mass flow rate. And from here we can get 1000 1.612 slug per second as mass flow rate. So here we have fx, which is only out. So this is for this condition when the body is stopping. Here we can think like, since it is not moving, we will not have anything out, or we will not have anything inflow. However, there will be air that will be going out from this propeller system. So it is just surrounding atmospheric air. So regardless of the motion, we will have out from this system. So since the velocity related to the boat is given as 100 feet per second in this propeller, we will still have 100 feet per second velocity. So even it is moving, we will have that 100 feet per second, and right now it is not moving, so we will still have that value. You can think this as like a velocity coming from air. And that's why we calculate mass flow rate using this velocity. So we have m dot v out, and this is 1.62612 times 100 feet per second. And this gives 161 pound force. And now let's look at when boat is moving. So again, we are going to use out minus in, and we can write it like m dot v2 minus v1. So it will be 1.612 slug per second. And this time differently, again, we still have 100, but since the boat is moving, we have 30 feet per second as inlet. So we will have 100 minus 30 feet per second. And this is giving 113 pound force. Let's solve the final question, which is 7.4. Here, we just need to select all that correct. So we will investigate units of energy and what it means. So we are going to just select it if it has same units, or if we can represent it with different terms or expressions. So first of all, energy is a property of a system that characterizes the amount of work. Power is rate of energy transfer. So it is actually energy by time. And also, actually these are all coming from page 228 and 9. You can find all these definitions. 1 pound force moving through a distance of 1 foot. So this is one of the definitions for energy. So it represents the force of 1 pound force moving through a distance of 1 foot. Or it is also defined as the approximate amount of energy required to increase the temperature of 1 gram of water by 1 Celsius degree. And actually there's a conversion between calorie and 4.187 joule. So basically, if you look at the options, we said energy is amount of work. So of course they will have same units. Power is rate of energy, which is energy over time. So we don't take this. In C, it says it has same units work over time. This is again power. It can have units of joule. This is correct. And also, as we mentioned, energy, it can be also used as calories, and there's a conversion between calories and joule. So G is also correct. And also with another definition, it has foot times pound force. So we can also use that. And when we look at E, it says units of watt. And this is wrong because this is also unit of power. So we can say power, power, and power.